Hi, my name is Steven. I am a junior student at University of Washington majoring in atmospheric science. Today I want to briefly talk about hydrological cycle of the Earth system. Every drop of water we observe moves through an endless cycle containing oceans, land, and atmosphere, and this is what we call hydrological cycle. This cycle redistributes water across Earth's surface and atmosphere, powering the ecosystem, influencing climate, and also sustaining our lives. Today I want to briefly introduce this concept with some physical equations for a precise discussion. This equation stands for the water balance of the surface. P stands for precipitation, and D stands for dewfall, which is the direct condensation onto cool surface. Precipitation and dewfall are two primary input of water to the land surface. E stands for evaporation. Evaporation and transpiration return water from the surface to the atmosphere, driven by solar energy, and usually is negative for global water balance. The delta F is the runoff term, so this is the water that flows over land into streams, river, and eventually back to the ocean or filters into the ground. So this equation ensures that all the inputs are minusing the losses of water balance so that it balances out all the changes in storage, illustrating the conservation of mass of the surface in terms of water. When we assume negligible water storage and small dewfall during the whole water cycle, the net balance equal to 0 and dewfall merges to the precipitation term. Then the runoff will be approximating the precipitation minus evaporation. So this directly shows how excessive precipitation becomes the stream flow out of the water cycle. And this is the steady state equation for groundwater balance. There are also water balance in terms of atmosphere. Evaporation adds moisture into the atmosphere, forming the clouds, and the clouds produce precipitation, and dew will form on the ground, so this moisture leaves the atmospheric column. The delta FA is a new term. We call it horizontal transport because atmospheric winds move the moisture horizontally and redistributing the water vapor between the regions. So it's also a kind of runoff of water from the hydrological cycle, but just from atmospheric view. This balance equation accounts for the moisture removed by precipitation and dewfall, moisture added by evaporation, and net moisture gained or lost through horizontal transport wind. So this explains all the sign changes. Under steady conditions, the atmospheric water balance is negligible. So we rearranging the formula, what gives the evaporation is equal to the precipitation plus dewfall, and also the net transport. So this reflects the close link between local and large-scale atmospheric process. Globally, the hydrological cycle continuously moves water, balancing inputs and outputs in sustaining ecosystem and climate. Regions where evaporation exceeds precipitation, for example, tropical deserts experience net moisture loss from the atmosphere, which means they have large number of delta F, often requiring the import of water vapor via atmospheric circulation for precipitation to occur. Conversely, areas of net precipitation, for example, tropical rainforests, exports the net moisture back to the atmospheric cycle through evaporation. So this contributing to regional and global circulation patterns. The water runoff term, the delta FA, also captures all the mechanisms such as advection of moisture by wind. They are essential for phenomena like monsoon and mid-latitude storm tracks. So therefore, understanding water balances helps us to manage water resources, predict floods and disasters. This also ensures sustainable supply for agricultural, industrial, and households. Next time it rains or the sun rises, remember that this is a part of a hydrological cycle. This is our planet, one of the most important way to renew and redistribute the most important resource of our life, the water. Thank you.